So, even going further with complex numbers, the focus of this lesson is looking at the geometric interpretations of different operations with complex numbers. And let's start with this. I have a number in Cartesian form, -1 plus root 3i. So let's sketch this first. And I'll draw it here. And I'll try to make it vaguely to scale. -1 plus 3, so 1 to the left, roughly root 3 up, a little bit more. I don't know, something like this. So -1 comma root 3. And so the vector looks like this. Okay, and that is complex number z. All right, so we want the Argand diagrams for a variety of things. Well, I've got one done for z. I want for the conjugate of z. And so let's remember that the conjugate of z, in this case, would be -1 minus root 3i. So in terms of the visual, it would have the same x coordinate, but the y would have the opposite sign. So it just ends up being a reflection about the x-axis. And so I'll try to do my best to visualize it like that. There we go. Oddly wavy line considering I'm using a ruler, and that is z with the asterisk, the conjugate of z. Keep in mind these angles here are the same. And then I have minus z. Well, in this case, minus z would be all of this times -1. So it's +1 plus root 3i. And that should be, geometrically, that should be the same vector but going the opposite direction. Don't know why my ruler is giving such wobbly lines. I'm going to grab a new ruler. Actually, I'll try the other side of it. I don't think you actually care. Oh, no. There we go. Take 2. That never happened. There we go. Still wobbly, but at least it's there. And that is minus z. And finally, I have 2z. And so 2z is just 2 times what I had. So it'll be -2 plus 2 root 3i. And so geometrically, it would be the exact same vector as z, just twice as long. And so I'll just kind of eyeball this as looking something like this, and then twice as much to there. Writing on top of my own work, the coordinates at that point would be -2 and 2 root 3. All right, there's my geometric approach. And keep in mind, in general, the conjugate is always going to be a reflection around the x-axis. The opposite, if you just change z to minus z, it'll always be going the opposite direction. And when you multiply by some coefficient, it'll just stretch it by whatever that coefficient is. Lastly, I want all of these in polar form. And so for this, all I really need to figure out is the modulus of my first vector as well as that angle. And so pretty quickly I can see that the length of z is 2. And using things we've done before, we have a special triangle here. That angle is exactly pi/3. And so therefore, in polar form, z would be 2 times CIS of this angle right there, which would be 2 pi/3. Alternatively, in Euler form, it would be 2e to the power of 2 pi/3 times I. I won't do that for every one, though. The conjugate has the exact same absolute value, exact same modulus. Just the angle is different. This time we're looking this way. So it's -2 pi/3. The minus z will have, again, same absolute value. This time looking at this angle right there, so minus pi/3. And finally, where I stretch this to z, will have twice as long of modulus or an absolute value, but the same angle as the first one. And obviously, at this point, I could write each of these in Euler form really quite quickly. So I'm too lazy to do that. All right. What I have here are two vectors, and I want to geometrically show the sum of these two vectors and the difference. And so let's look at A plus B. And first, actually, I'll figure it out numerically and then show how this compares to, actually, no, I'll do it geometrically first, then I'll get to the algebraic work later. In general, when you're adding two vectors, it doesn't matter, or adding two complex numbers, but these are vectors here. It doesn't matter which order you add them. And so there's a few ways we can look at it. Let's say if we think about A first, because I think I do have A written first, A plus B, yep. We can imagine this vector here, imagine it starting from here and going like this. And so we'll talk more about vectors later in the course, but we kind of sometimes call this, when you're adding vectors, the tip of one vector to the tail of the other. Or I should say tail of one to the tip of the other. Anyways, if I look at this vector and I've highlighted in blue, it goes down 1 over 6. So that shows me how this vector changes. So I'm going to kind of imagine that from here going down 1 over 6. And it should end up right here. And so that point, and again, what I'm showing you here, I'm imagining that vector just starting at the end of vector A. That point there shows me where the sum of these ends. And so my answer is this. It's this vector right here. And so that is A plus B, which I can just see by looking at it is 5 plus 2i. Another way of looking at this is to imagine these two first vectors and imagining a parallelogram between them. So going back to the tip of A here and imagine that same vector from the origin to B, starting from here and kind of imagining it, it would look like this. And same thing for the first vector A. Imagine it being right here to create a parallelogram. And the sum is just the diagonal across it. That's it. I kind of think it's probably just easier to imagine one vector being starting from the other, but it's all the same idea. Either way, there's a geometric approach. If we're subtracting these two vectors, the order matters, and so it's going to be A take away B, and maybe I'll just label the A a little more clearly here. Here's my A. And so I want A minus B. So keep in mind, A take away B is the same as A plus minus B. And so I can use the ideas as what I did in the first question, as long as I think about adding negative B. And like we saw before, minus B is the same vector we see here, just going the opposite direction. So minus B looks like this. It goes all the way, it's at negative 6 comma 1. So this is minus B. And so I'm going to erase some of my previous drawings from here. Oh, come back. Okay, and so if I want to add these two together, I can do the same idea as what I did at the beginning. I can imagine a parallelogram. I'll draw it a sketch quickly, and it'll be the diagonal of these. Or what I actually kind of prefer is just take A and this vector of minus B, just start it from the tip of A. So I go up 1 over 6 to the left. And so if I imagine go up 1 and 6 to the left, I go just a little bit off my page here. But I can tell this point here will be at negative 7 comma 4. Which means the vector I know is minus 7 plus 4i. So I know A minus B equals minus 7 plus 4i. And so lastly, it does ask to write each of these in Euler form. We've done that sort of stuff a lot, so I'll just pretty much jump straight to the answer. But those are the two in Cartesian form. And so in Euler form, A plus B, again, I'll start with 5 plus 2i. At this point, we've talked about this many times. Feel free to use your GDC if you're not asked for an exact value. You get root 29 for the absolute value times e to the angle in radians of 0.381 times I, or if you just decimalize everything. And again, quite often we are okay with just 3 significant figures. I get about 5.39 times e to the 0.381 I. That's it. And similar, a minus b. In Cartesian form is exactly negative 7 plus 4i. Euler form, I'll just go right to the decimal approximation, approximate 8.06 e to the 2.62 I. And we will later on in the course focus on vectors more, and this idea of adding and subtracting vectors like this we'll see more. So the more we understand this now, the easier later parts of the course become. Lastly, I want to look at a geometric understanding of multiplication and dividing with vectors. So I have the diagrams for A and B here, and I want to visually try to understand or see the connection between the algebraic or numeric work and the geometric interpretation of when I go A times B or I go A divided by B. So maybe let's first just do the numeric approach for A times B. So if I look at A times B, in this case, I'm going to write it in Euler form. So A in Euler form is 4e to the negative 5 pi over 6i times B, which is 2e to the negative pi over 3i. All right, and so like we've seen before, I can just multiply 4 times 2 to get 8. And then I can multiply these two together, in which case I just add my exponents because they have the same base. So I get e to the negative 5 pi over 6 minus pi over 3. Finding that common denominator, making that a 6, making that a 2, I get negative 7 pi over 6 times I. Now, negative 7 pi over 6 is beyond our usual angle and standard position we want. So, because that goes more than half a rotation backwards, and so we really should write this as 8e times positive 5 pi over 6i. But they end up in the same spot. So geometrically, let's think about what happened here. Well, first, where did this 8 come from? Well, that was just the length of these two being multiplied to each other. So my answer is, whatever the lengths of these are, just one times the other, the order doesn't matter. That represents the modulus or the absolute value or the distance of our new vector. But the angle, this 5 pi over 6, where did that come from? Well, really, I added these two angles together. They're both negative, but still I added them together. So if I look at my diagram here, from here to here, that is again minus 60. I'll go in degrees for a second, a little easier to describe. And from here to here, this is negative 150 degrees. So when I multiply these together, the new angle is just these two added to each other. So it's negative 150 plus another negative 60, which brings me all the way to here, roughly. And notice that angle from there to there is positive 150 in degrees. In radians, that's 5 pi over 6. So really, the rotations are being added to one another. And the length of this, which is 8, I'll just roughly sketch it like this, is just found by the length of those two vectors being multiplied to each other. So when you multiply two vectors, the length of it is just simply the length of the individual vectors being multiplied to each other. The angle of it is the two angles being added to each other. And so there's my rough little sketch of where this is. Okay, and again, that represents A times B, which I have exactly written there. And so for A divided by B, very similar idea, A over B. So I have 4e to the negative 5 pi over 6 times I divided by 2e. Negative pi over 3 times I, same idea. I'm now going to divide my lengths of these vectors, the absolute value, whatever. I get 2. And then since I'm dividing these, I'm really just subtracting my angles. And so it's 5 pi over 6 minus negative 2 pi over 6. So negative 5 pi over 6 plus 2 pi over 6, which is negative 3 pi over 6. Which times I, we realize, is negative half a pi. So let's now find the geometric approach to that. So if I go back to here, maybe I'll clean up all my mess from before. So the length, now the order wouldn't matter, is a divided by b, so it's 4 divided by 2. So the length of my final answer will just be 2. The angle, though, will be my first minus the other. So it's this angle, which again, I'll stick with degrees for a second, just because the numbers are a bit nicer, negative 150 degrees, minus this angle, which was, again, this was minus 60 degrees. So imagine this angle here, instead of being rotated 60 degrees more there, it's being rotated 60 degrees this way, which brings me right to the x-axis, and we get something going straight down. And keep in mind, the length of that line is exactly 2, so I can visualize this quite nicely. It's just right there. And so, since this is such a nice, easy one to draw, even though I don't ask for it in Cartesian form, please realize that 2 times e to the negative pi over 2I, I can see it's just the same as negative 2I. I can see from my visual right here, it's negative 2I. There is no real element to it. So that's it.